So now I would like to invite our last speaker, Gina, from CLS in France. The topic is EDFix, an algorithm for the comparison and the validation of fixed ambiguities. Please go ahead.
Okay, thank you very much. Hello, everyone. My name is Gina Katsigianni. I am a member of the CNES CNLS Analysis Center based in Toulouse, France. And together with my colleagues, Sylvain Loulaye and Alvaro Santamaria, we would like to present to you a new idea and an algorithm for the comparison and validation of phase-fixed ambiguities. Here I will give a brief overview of the talk. I will address the main key questions that we have nowadays with ambiguity fixing. Then I will describe the EDFix algorithm itself. And then I will show two applications. One by example of precise orbit determination and global network solution. And the second one is an example about PPPAR solutions. Since the beginning of integer products, we aim to address the following questions. Is the ambiguity fixing correct and reliable? Can we really trust it? When ambiguity resolution fails, can we identify where and when it happened beyond the overall ambiguity fixing rate? And when fixed ambiguities are common in 2 consecutive days or 2 common solutions, are they consistent? And to address this question, nowadays we use a variety of statistical indicators and validation tests. The global percentage of ambiguity fixing, which is widely used nowadays, success rate, ratio tests, residuals, etc. And we also know that an incorrect ambiguity fixing can have a significant impact on the GNSS product's quality, and this is seen through the orbit overlaps and the clock overlaps of the measurements. In addition, for comparisons and combinations of the IGS GNSS products delivered by different analysis centers are performed by either through individual product comparisons, like in the legacy IGS final combinations, or through combined analysis of all GNSS products as a whole data sets of data, as done, for instance, by the BAR working group and WCC experimental combination of PPPAR products, typically using global daily statistics. However, these two methods mostly use the global ambiguity fixing rate as their main metric of validation, and this information is not complete. The same ambiguity fixing rate in 2 solutions does not necessarily imply the same integer values. And we also do not know when and where a problem might have occurred. So in order to address those systems, we come to the key question. When fixed ambiguities are in common in 2 consecutive days or in 2 processings, are they consistent with each other? So to overcome with these issues, we have thought of an algorithm in order to check the agreement between 2 different integer ambiguity solutions. Okay, I'll take it over. So the idea for what we had is to compare the agreement between 2 different ambiguity solutions with common passes at the level of each individual satellite station passes. And this can be done with 2 ways, either by comparing 2 successive days that have common passes, and we can have, for example, some kind of ambiguity overlaps, or by comparing the same day with different processings. But at this stage, a direct comparison is not straightforward, and I will explain to you why. Let's say that the satellite is visible by many stations. Then there is a part of the past integer cycles, let's call it arbitrary n number, that is common to all the stations. And in the same way, when a station observes multiple satellites at the same time, there is a plus m arbitrary number that is common to all the satellites. And without any constraints, we can, for example, organize all our satellite station passes into matrices. Let's say in this case, I can put all the stations in every rows and all my satellites in every column. So as we saw before, for each satellite, we have this common n arbitrary number, and in the same way, for each station, we have this common arbitrary m number. So let's call this our solution A. And if we get another solution, let's call it solution B, with the same common passes, I can organize them in the same way in my matrix, with the only difference that in this case, my n and my m numbers are not the same. They are, let's call them n prime and n prime. And a nice metaphor that I would like to keep in mind when thinking about these things is the one of the Rubik's cubes. As you see here, if I compare these two cubes directly, they're not equal, but they're still the same cube. So the idea is to find the right transformation to pass from the one to the other. And not only this, the most important thing is to be able to identify where an outlier is happening, which means which satellite station pair has inconsistent ambiguity fixed values. And as I explained before, a direct comparison is not possible. We need also to take into account the following equations. Here is the case of the undifferenced ambiguity fixing that is done in 2 steps. The first step is to fix the wide line ambiguity. Yeah, okay. By applying the OSB biases to the Melbourne-Rubin linear combination. And the second step is to fix the narrow lane ambiguities by forming an ionosphere-free linear combination of the carrier phase. So as you see here in my equations, all these terms marked in orange, they are highly correlated with the ambiguity, and therefore I have to take them also into account. Here I will describe briefly my algorithm. So we have a step of pre-processing. We take the two solutions, A and B. We find the common passes. We compare all these terms that I showed in orange before in order to construct the matrices A and B. And later, I take the difference of these two matrices, the matrix C, and I apply an iterative process where I find the most frequent number for each station and each satellite, and I subtract it for the whole line. And this is looping until the C matrix does no longer change. And at the end, I get my results, which can be either global statistics or all the individual satellite station passes that I see the inconsistencies. So let's have a look at our first example. In our analysis center weekly processing chain, we use IDEFIX daily ambiguity overlaps in order to assess the quality of our final products and global network solution. The ambiguity resolution method we are using is the integer bootstrap, and here I will show you 4 months of ambiguity overlaps comparisons for GPS and Galileo. And when I'm talking about overlaps, in our analysis center, we extend the days by plus or minus 6 hours, and this gives us a 12-hour overlap window in order to see our tests and our validations. So here is an example of the global percentage of differences of inconsistencies using ambiguity overlaps. As you see, we have generally a perfect agreement between successive days with a few inconsistencies. And for instance, if I want to go and check more into detail in one of these peaks, I know which are these passes, and I can go see and have a better look. So here's an example of a pass, the measurement residuals of a pass that had ambiguity inconsistencies for 2 successive days, shown here in black and in red. In general, measurement residuals may indicate either a problem in measurements or a problem of processing algorithms. For instance, in this case, in this example, we see that we had an undetected cycle slip, an additional noisy final part for the pass of the second day. And for instance, this is a case where this pass should not have been fixed at all. And for the example of PPPAR processing, we tried to reproduce as closely as possible the comparisons done by the BAR working group. We processed a network of 10 stations And we did processings for 10 days for GPS with products of GRG final, GRG MSX final, code final, and WCC final. The idea here is to compare the different processing strategies and detect the agreement between ambiguity resolution. And here you can see in each line here is a comparison between two processings. Here are I show the differences of fixed ambiguity values. In general, we have a perfect agreement between different processings with a few inconsistencies. And again, if I want, for instance, to go and check more into detail, I can. Here is an example of the output that we have in our screen. We have the position of the ambiguities differences in the passage matrix. We can have the number and the name of the passage ID as long with the magnitude of the difference expressed in integer cycles and some global statistics. So here in this presentation, I want to show you a new idea. It is possible to compare ambiguity resolution results in order to detect common passages with inconsistent fixed ambiguities between two solutions. This can be done either through ambiguity overlaps or comparison of different processings or two analysis centers, for instance. With this algorithm, it is possible to go deeper into the level of individual passes in order to detect possible problems. And we believe that this might be a helpful tool in order to detect the local anomalies in the products, and it can help also the consistency and continuity of the analysis centers combinations. We also think that it would be very helpful in order to assess and improve the continuity of the integer bar combined products. And this is all from my side. Please feel free to contact and meet us in the poster section if you want to learn more, or you can also email us at the email that you see there. Well, thank you very much for your attention.